Hi everyone, my name's Ellen. I'm a process engineer at Extracellular, and as mentioned, I'm going to talk to you today about how Extracellular developed a continuous process for the production of quail muscle cells. So we started by using the DASCIP system, working with 1 liter bioreactors at an 800 milliliter working volume. We developed the batch and the fed batch process, which generated between 7 to 10 grams of biomass. We then did a repeat batch process where we harvested 40% of the biomass daily, generating in total around 30 grams of biomass. And then we did 2 perfusion processes, one standard perfusion process, generating around 70 grams, and finally the continuous process, which, as you can see, generated 321 grams of biomass from an 800 milliliter vessel. And so why did we do this? So our aim was to develop a process that is, 1, sustainable. So that we can run a process continually for months on end. That is also scalable, so we wanted to limit the vessel volumes of media per day, perfusing through the system to 2, so that we can do the proof of concept at 1 liter and then scale this all the way up to the 2,000 liter scale without significant issues. And we also wanted to make this process efficient, so we used key automation tools in order to reduce our workload when running a bioreactor for a prolonged period of time. So this was our starting point. So first off, we ran the batch and the fed batch, and as you can see by the blue and the green lines, both of these processes had very similar outputs, and the cells plateaued between 4 to 5 million cells per mil, mainly due to nutrient depletion or waste metabolite accumulation. However, we see with the perfusion process that when we increase the vessel volumes a day up to a maximum of 6, we can increase the cell density in the bioreactor tenfold, up to 50 million cells per mil, and increase the biomass 5-fold, so reaching 100 grams a liter in a single vessel. By increasing the perfusion rates to a maximum of 6, we saw that with the metabolites where we measured glucose, lactate, glutamine, and ammonia, we were able to keep all 4 metabolites in an equilibrium within the system. In the perfusion vessel, we also used the ABA capacitance probe, which is an online measurement of cell density. And as you can see in the line in black, we had an online measurement that was pretty bang on with our sampling points. This capacitance probe also gives us a reading every 30 seconds. So between sampling points, we have a really nice idea of cell proliferation during this process. However, like the batch and the fed batch, the perfusion bioreactor also had limitations. And so as you can see from the online process data, high-density cell cultures proved much more difficult to control. The limiting factor in this process was the oxygen transfer. So you can see in the blue line here, we saw a crash in the DO around 180 hours due to the high cell densities in there. We also saw a lot of temperature instability. So once our perfusion rates were between 5 and 6 VVD, it was very hard to control the temperature at 37 degrees inside the vessel. And like I said before, with the high perfusion rates, this is a very media inefficient process. So we used 21 liters of media perfusing through the system over the course of 11 days to reach our final titer of around 70 grams. And again, with a high perfusion rate, this is not something that is scalable up to the 1,000 liter scale, because you can imagine trying to hold 6,000 liters of media a day in a room in order to run this. It's not really an option. So it led us to think, where do we go from here? So we decided to develop a continuous process. So we used the perfusion data to provide key insights to define sustainable set points for our continuous process. We started off by thinking that we wanted our wet cell weight in the bioreactor to be around 30 grams a liter. So by harvesting 50% of the bioreactor continually every 24 hours, we would harvest around 15 grams a day. And this corresponds to somewhere in here around 10 million cells per mil. In terms of the capacitance, we're looking at a capacitance reading of around 30. And in terms of the other set points that we needed to define, as I said before, we wanted to limit our VVD to 2. And also we saw that in the perfusion process, the glucose had to be above 1 gram a liter, as we didn't see any negative impact on the doubling time when the glucose concentration was above 1 gram. So by combining all of this information that we got from the perfusion process, we were looking at our data points from around 120 to 150 hours of that process. And that kind of gave us a really good starting point as to where to look to develop the continuous. And so this is what we came up with. So this is our continuous process at Extracellular. And as you can see here, so this is our 1 liter vessel. We're using the single-use BioBlue 1Cs. And it's connected to an ATF2 membrane. You then see this is the harvest pump. So the harvest comes out of this bioreactor and into a harvest bottle. We also have a media fill pump and a media out pump for the perfusion rates. And both the bioreactor itself and the harvest pump are on scales. And so this is more talking about how we actually achieved this. And so automation was a really important factor when we were developing the continuous process, because it allowed for a stable process and a flexible process during the 36 days that we ran this. So first of all, our media fill pump was automated and connected to the weight of the bioreactor. So as I mentioned before, our bioreactor was on a scale, and so whenever the bioreactor dropped below our minimum set point, that pump would automatically kick on and refill the bioreactor with fresh media, meaning that we didn't encounter any volume issues when we were doing this process. The harvest pump was also connected to the capacitance probe. So when we set our minimum capacitance reading, as soon as the cells proliferated to that set point, the harvest pump would kick on and slowly start removing cell suspension from the bioreactor. And so what that means is if your cells in your bioreactor have a 24-hour doubling time, you're going to take 50% of that bioreactor, 50% of the cells over a 24-hour period. If your doubling time is faster, you'll take more. If it's slower, you'll take less. And this was our outputs. So as you can see, I've chosen a really poor color with a yellow thin line on a white graph. But if you look at the yellow thin line, you can see the set point. And our green line is what our capacitance was actually at. So as you can see, using this automation, we can create a super accurate process for controlling cell density. And you can see in the blue line at the bottom, so this is our harvest pump. So you can see that the harvest pump was continually on throughout the process, apart from when we increased the capacitance set points and allow the cells to proliferate. So you can see in this time of proliferation, the harvest pump was switched off. So this was the output. So you can see at the beginning of the process, we allow the cells to proliferate exponentially up to a cell density of around 12 million cells per mil, at which point we initiated the harvest and brought the density in the bioreactor down to around 8 million cells per mil. We then held this cell density in the bioreactor for approximately 2 weeks before we had to do a media dropout and drop the density to around 5 million cells per mil. Over the course of the following 2 weeks, we could then increase the cell density back to our original 8 million cells per mil set point. So why did we have to do this? Well, if you have a look at the metabolites on this side, you can see that over the course of the first 2 weeks, we see a steady decrease in glucose and a steady increase in lactate until we reached a kind of critical point at around day 25, where the glucose dropped to 0.3 grams a litre and the lactate spiked to around 5 grams a litre. And it would be at this point in a conventional bioprocess that we would have to call it quits and harvest because we've got the maximum output out of our vessel. However, with the automation and the flexibility of this process, we were able to do a 50% cell dropout and replenish with fresh media in order to kind of reset and rebalance the metabolites that are in the bioreactor. And you can see the results here. So the glucose shot back up to around 3 and the lactate dropped to around 2 in order to keep this process going for a further 2 weeks. And then over the course of these 2 weeks, we could increase the capacitance set point back to where we started. And interestingly, what we see is that we don't see that crash in glucose and the spike in lactate that we saw at the beginning. So it's almost as if these cells are being weaned into conditions that have lower glucose concentrations and higher lactate concentrations. And what you see here is that despite all of these changes, whether that be cell density or whether that be different metabolite concentrations, we don't see any significant impact on the doubling time. And so the doubling time throughout our whole process was 24.5 hours. So what did this look like? So over the 36 days, we managed to produce 320.8 grams of biomass from an 800 milliliter vessel. In total, we used 66.2 liters of media, which roughly estimates at 1.8 liters a day. So sticking within our 2 vessel volumes a day that we intended to use in order to scale this process up. Not only did we see no changes in doubling time, but we also didn't see any changes in cell morphology. So you can see the cells at day 0 and day 36. Morphology is very similar, and we managed to keep the viability above 90% for the entirety of our process. And as you can see on the right-hand side, this was our harvests over the course of the process. So we started harvesting on day 10, And our process for that was we took out cells from the bioreactor continually over 48 hours, and then did the manual harvest every 48 hours. So you can see our individual harvests over the course of that time period. However, the continuous process isn't perfect either. And your optimum bioprocess for cultivated meat production is going to be dependent on a lot of things. For example, media costs. So if you have a really expensive media, you want to make sure that you are getting the maximum output out of that media, maybe perhaps using something like the batch or the fed batch. Because as you can see here, the biomass conversion from this process, which is the grams that are produced per litre of media you're putting into that system, are a lot higher. However, with the continuous, with time and equipment use in mind, although the biomass conversion is slightly lower, to produce the same amount of biomass that we produced using batch or fed batch processes, you would have to run 31 batch processes, which would take you around 200 days. And I know this industry is in a bit of a rush to get results, so no one's got time for that. So the work is not over, and so where do we go from here? So obviously, as been mentioned before, media cost is a huge issue, and the lower your media costs, you can put more into your process. There's less of an issue using 2 VVD a day when you can reduce your media costs. Similarly, with cell line stability, if you're running a process continually, you need to make sure that your cell line has the proliferative capacity to be able to kind of run with your process for a long, prolonged period of time. And also with media stability. So our media that we were using is stable at room temperature for 1 month, so we didn't see any stability issues during the process. But obviously, if you have media that is stable for a less amount of time, it's definitely a consideration that you have to take into account. And I guess all of this leads to point number 4, which is scale up. So with these 3 things in mind, it would then be possible to take this process and scale it to the 10, 50, 2,000 litre scale. And at a 50 litre scale, it is possible to be generating kilos, tens of kilos of cultivated product. Which leads me to say thank you. Thank you to my incredible team who has been amazing at helping us all achieve this. And yeah, if you've got any questions, feel free to come and chat to myself or Ben and Moses, who are also here today. And yeah, I'm happy to answer a couple of questions if you have any. Thank you.
Thank you. We have time for a couple of questions. So one question here, over here on the left here.
Congratulations for the work. I have a question regarding, or maybe 2 questions. What do you think is the maximum scale with your system that you would consider this to be doable? And then the second one is, what is your considerations if you were to integrate a differentiation step into this sort of setup?
Yeah, great questions. I guess in terms of the scale, I think where we are in an industry at the moment, we feel like this process, we designed this process in mind to be able to be run at the 2,000 litre scale. With a 1,000 litre working volume, we can do 2,000 litres of media a day, and that is something that in our current facility we have capabilities to do, which is why we designed this process in mind, to be able to use all of those processes at the 1,000 litre scale. I guess in terms of scaling it further than that, with things like media optimization or creating a kind of enhanced substrate in your media, it would be possible to reduce your vessel volumes a day, say from 2 to maybe 1 or even lower than that. And so when you're working at kind of higher scales, the 10,000 or the 50,000 litre, it might be possible to just put enhanced substrates into your media fill line, and that would be able to reduce your vessel volumes a day and therefore make that process even more scalable than it already is now. And I guess in terms of differentiation as well, it is something that we have also been thinking about. And if I go back to the setup, what the idea for being able to differentiate in this process, so if you have your proliferation bioreactor here, instead of your harvest pump going into a media bottle, it'd be possible to do your harvest pump going into a differentiation bioreactor. The nice thing about the DASCIP is it's a parallel system, so we can run multiple vessels all at once. And so I guess the idea for this would be to have a single proliferation vessel that you can continue for months and multiple differentiation bioreactors that would be run in a batch or a fed batch mode. So you'd be able to swap that cell suspension into your differentiation media and do your differentiation for whatever period of time your cells require, while continuing to grow your cells in the continuous bioreactor.
Thank you.
One final question in the back or in the middle.
Thank you. A really impressive talk. I wonder whether you can describe a bit more the culture medium. Is there any growth factor present, and do you have to change the concentration?
Yeah, so this culture has FGF2 in it. It's the only growth factor. We did a bit of media optimization in order to reduce the concentrations and also the growth factors required in the media. This has, FGF2 in it, and it's the same concentration throughout the whole process.
Okay, I think we say thank you for your nice talk.